Testing, testing. Everybody hear me all right? Thumbs up from people on the edges. Very good. All right. Hi, guys. Welcome. Very glad to have you here at our first lecture series of the fall 2023 semester. So thank you for being here. My name is Ben. I'm the outreach coordinator for CAS for the 2023 to 2024 year. But more importantly, our lecturer tonight is Annika. Annika is a longtime CAS member, our former president for last year, and a good friend of all of ours. She spent her summer doing research at the National Radio Astronomy Observatory, and she's just done a lot of research in the past, so she's very knowledgeable on these things. And she's going to give us a very nice lecture tonight, and hope you enjoy. So I hand it over to Annika. Oh, and by the way, one thing, just keep your questions for the end, please. And to anyone on Zoom, we have a Q&A bar. You can put your questions in that, and we'll handle them towards the end of the lecture. Thank you.
Thanks so much, Ben, for that wonderful introduction. Yeah, hi, everyone. Like Ben mentioned, my name is Annika. I'm a senior undergrad, of course, CAS member. I've been a member of CAS since my freshman year. And yeah, this summer I had the really, really wonderful opportunity of working at the National Radio Astronomy Observatory. It was a great experience. So today I'm going to tell you a little bit about the work that I did there. So yeah, let's get into it. So yeah, I'm going to talk today about the resurrection of a type 2L supernova, SN 2018 IVC, and what its resurrection can tell us about binarity as a potential explanation for the mass loss history of very, very high mass stars. So I said a lot of jargon in that sentence. And so hopefully throughout this presentation, we're gonna kind of unpack what that really means. So let's get into it. There we go. Okay, so yeah, the outline of this talk is gonna go something a little like this. We're gonna give some background on supernovae and then our specific supernovae, which for the rest of this talk, I'm no longer going to call SN 2018 IVC because that's a bit of a mouthful. I'm gonna call her CC. We'll talk about why in a couple slides. So yeah, foreshadowing. So then we'll go into the actual observations that we had to study this supernova. We'll look at what we got from those observations and what sort of modeling we can do with those observations to say something about some of the actual physical parameters of the supernova. And then I'll just sum up and talk about where this project's going in the future. So let's get into it. Yeah, so before we can get into all those big jargony words I said at the very beginning, we have to take a couple steps back and just talk about what is a supernova. So a supernova is an explosion at the death of a star. These events, I want to emphasize, are really, really, really energetic events. They're equivalent to the energy of 1 billion, 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 billion tons of TNT. If you are someone who is a little bit more Minecraft minded in this room, if you were to fill an entire world with only TNT blocks in Minecraft. So this picture is a bit of a, this picture is deceiving because there's other things in this picture that are not TNT. You would need to fill the whole world with TNT. If you did that and you took 1 billion billion of those worlds, that would be an equivalent amount of energy. So we're just talking huge energies. If you want a more sciencey number, it's the order 10 to the 53 ergs. And frankly, actually, most of that energy gets carried away in neutrinos. These are neutrino-producing events, and it's about 90% of the energy actually gets carried away with the neutrinos, and what's left over is the electromagnetic energy, which is what we can see. And yeah, so which is still like a very, very high energy, but it's quite remarkable that we can see them so brightly, but we're not even seeing most of that energy because it's getting carried away in these elusive neutrinos, which we have a hard time detecting. So yeah, so there are two primary types of supernovae. If you want to speak very broadly, there's thermonuclear supernovae and core collapse supernovae. So the thermonuclear, those are the supernovae that you'll have a white dwarf, it will become very unstable, and the shock wave will travel through the star and tear it apart completely. It leaves no remnant behind. Those are type 1A supernovae, if you've heard that. You may have heard that term before. The other type are the core collapse supernovae. So that's when we have a really, really high mass star, at least 8 times the mass of our sun or higher than that. You can go as high as you wish, I guess. And the core will get very massive, and the gravitational pressure will cause it to sort of implode. And this will send a shock out, create an explosion, and you'll be left with a remnant. And core collapse supernovae are very interesting because they give us an opportunity to sort of peer into the history of the original star that was left over. There's sort of these windows into the past. And I'll tell you how that works. So you see here, I wrote these two numbers, V wind, 10 kilometers per second, and V ejecta, 10,000 kilometers per second. So these two speeds, this first one is sort of the general order of the speed of the material that is lost from the original star before it's exploded. Then the star explodes. We have this material that's traveling super fast. It's traveling 10,000 kilometers per second. And so it's going to start catching up to all the material that was lost in the star. So as we look at this supernova after it's exploded, we'll look for some time. And when we look at that time and we see some brightness, we'll say, okay, that's something that's going on that was 1 day before the explosion. And then we'll keep looking, and we'll be able to figure out what was going on 1 year before the explosion. And then we'll keep looking on, and we get to 10 years, and you can go out to thousands of years to even longer. And so you can really probe the history of high mass stars, which is a very interesting thing. And I'll mention one thing I should mention is that it's not coming from the explosion itself. It's in observing the interaction between the explosion and the surrounding gas. So now we've kind of talked a little bit about what a supernova is. Let's go specifically into the supernova that I studied this summer. So SN 2018 IVC, or CC, was a supernova discovered in November of 2018. The IVC, I'll just mention, that denotes how many other supernovae were observed in that year. So when they first started seeing supernovae, they would see few enough per year that just labeling them with the alphabet was enough, because they would never see more than 26. But then we started getting better and better telescopes, and we would just see these things all over the place. And so you end up with this kind of silly naming scheme where you get these very arbitrary names. But that's its name, but we're going to call it CC. CC is a core collapse supernova, and it's a type 2L supernova. So the 2 indicates that there is hydrogen present at the time of the explosion, and L means that there's a linear decay in the light curve. And so you'll see all these sort of different classifications for supernovae: type 1A, type 2L, type 2P, all of these. These classification schemes are actually very much an unsolved problem in stellar evolution. They are our best attempt at describing the phenomena that we see from the supernova, but they don't necessarily implicate anything about the actual state of the original star that the supernova came from. And so there's still a lot of questions to be answered with this classification scheme. So I'll just mention that as a side note. It's at a distance of 10 megaparsecs, which is around 30 million light years. And that is actually very close when we're talking about the entire universe. This is something that's in our local universe, basically. We're not talking about anything cosmological here. And it turns out that the host galaxy of this supernova is actually a Messier object. For some of our cast members in the room, we like to search for those. So it's M77, which is also known as the Squid Galaxy. And M77 is a very, very bright galaxy. And it, in and of itself, is actually something we call a megamaser, if you're curious about that. And it's something really interesting to study on its own, but we're trying to look at the supernova that's in it. So why are we trying to look at the supernova? Why do we care? So you would kind of expect that if we look at any supernova over time, it's going to get fainter and fainter with time. So this figure I show on the right is from a paper that was published earlier this year looking at CC. And they have data from all the way from like 4 days after the explosion to around 200 days after the explosion. And so you can see on the x-axis, this is time. On the y-axis is brightness. And as time goes on, the supernova is getting dimmer and dimmer, which we kind of expect. But then around 1,000 days after the explosion, they went and looked again to see, okay, what's CC up to? And what they saw was this very dramatic departure from the expected decay of the supernova. And they saw it in both of the wavelengths that they looked at. And so this was quite interesting. This is quite a rare thing to see. And it indicates that, so we'll get into it a little bit more later, but the emission that we see in the radio wavelengths is coming from the interaction of the explosion with the surrounding gas. And so when they saw this extreme rebrightening here, that's, I don't know if you can, yeah, you can see my mouse, but these 2 points here, they say, okay, this must have been coming from an interaction with a much denser medium than the explosion had previously been sort of interacting with. And the standard explanations for mass loss from high mass stars, which come from the radiation pressure from thermonuclear reactions, are not sufficient to create such an extreme mass loss rate that would create such dense environments around the stars. So they knew something else must be going on. And oh yeah, here I just kind of, this plot, you know, sometimes looking at plots is not very enlightening. So just to show you actually how much brighter it got, you could see it in the images. So this top image is the supernova at 200 days post-explosion. The bottom image is at like 1,300 days post-explosion. And you can just see how much brighter it is by the fact that it gets bigger and it's red now. So yeah, it had this very dramatic rebrightening, and this paper, these folks that published this paper, their best explanation was that there must be some mass loss in the original star coming from a binary interaction. So this original star had a binary companion that was contributing to the mass loss of the main star. And so as you'll see, this binary interaction creates this dense shell sometime before the explosion. The explosion happens, and then it eventually meets up with this very dense shell, and that's the time at which we see this rebrightening. And this was their primary explanation for what they saw, and it's a very well-supported idea. There's a paper in 2012, a very important paper that did a survey of the high mass stars in our galaxy, and they found that over 70% of massive stars will exchange mass with a binary companion in their lifetimes. So it's this phenomenon is something we expect to see in most of the massive stars that we look at. So it would be a very reasonable explanation for what's going on. All right, so great. So we have the motivation why we want to look at the star, or why we want to look at this supernova. We want to see if we can understand something about the history of the original star from the supernova, because the late stage evolution of high mass stars is something that's not very well understood. And this is a very rare observational case where we might actually have a chance to probe that history directly. So how do we actually do that? We need some observations. And to get some observations, we need a telescope. So the telescope that I used this summer for my observations was the Very Large Array. It is exactly what it sounds like. It is a very large array of 27 radio antennas. It's in New Mexico, and it's in this Y shape. It's out in the desert. And the benefit of having an array of telescopes as opposed to having a single telescope is that when you go to take an image of something, you can get a much, much finer image when you have this large array as opposed to having a single dish. And this is something called interferometry. And so we wanted to use interferometry to be able to get some very good images of the supernova. So what are the data sets we're actually dealing with? For this, this summer, I was dealing with two data set. You can kind of split the data I had into two sets. There's the first set, which was actually coincident with the observations from this paper that originally saw the rebrightening, but just at lower frequencies. And so this was in August of 2022, about a little over a year ago. The frequencies I mentioned here, it's around 10 to 40 gigahertz, which is sort of mid-range frequency for the radio wavelengths. And like I mentioned, it was at the same time as that higher frequency data that originally saw the rebrightening. And so that's really great because we can say, okay, was this going on in the lower frequency regime at the same time? And then the second data set is about a 1-year follow-up from that original data set. It's at the same frequencies, but importantly, it's in the A configuration of the VLA as opposed to the D configuration. Now, you probably can't see on these plots very well, but the D configuration, the X and the Y axis show the separation between all of the individual antennas. And it's is this one working? Here we go. Everyone can hear me again? Cool. Yeah, so this figure on the left, we see that all in all, the whole configuration is a couple hundred meters across. On the right, the A configuration, that's a couple thousand meters across. So it's the largest configuration of the VLA. The radius is around 1 kilometer. And so with interferometry and with arrays of radio telescopes, the further apart you put each of your individual antennas, the better and better your resolution is going to get, the better your images are going to be. And so this A configuration data, it's at the same frequencies, but importantly, it's much higher resolution than the first data set. So great, we have these observations, they were taken. And here I just show what we're sort of adding on from the previously existing radio data for the supernova. So all of the previous data was at much higher frequencies, around a couple hundred gigahertz. And with the VLA, we're looking on the order of 10 to 40-ish gigahertz. And just for a little refresher, or maybe for, to introduce to some folks in the room, perhaps, when I'm saying all of these numbers, 100 gigahertz, 10 gigahertz, so on, what I mean is the frequency of the light that we're actually looking at from the electromagnetic spectrum. So light can be thought of as a wave, and that wave can have quite a wide range of wavelengths. If it has a very, very long wavelength, we're talking about radio waves, the things that, actually transmit radio signals that we listen to sometimes, but also transmit really interesting astrophysical information. And then you go up in frequency, which corresponds to going to shorter and shorter wavelengths, and you get to X-rays and gamma rays, which are going to be much more energetic. So I just kind of, show the electromagnetic spectrum here. So when I'm talking, all of the data I'm talking about is all in the radio regime, but that's quite a wide bandwidth. Anything that's around a gigahertz, or around 10 to the 9 or 10 to the 10-ish hertz and less is going to be considered a radio wave. So so we have our observations, great. We're adding on to this previous data set in lower frequency regime, which there previously hadn't been any data for. But how do we actually process these observations? So like I mentioned, these images were taken through interferometry, and kind of in the most simple possible world, the 3 basic steps of processing an observation from interferometry go as follows. You edit the data. So you basically take out any of the data that isn't from the science that you actually want to do. Then you go into calibrate it. So calibration, how can I explain this? So when we have our telescope doesn't directly give us the brightnesses of the thing that we're looking at. So what we need to do is go to some object whose brightness we know really, really well and compare the values that the telescope gives us when it looks at that object to the values it gives us when we look at our target object and say, okay, based on that comparison, this is how bright our object actually is on the sky. And so once we've done that calibration, we go on to the actual imaging. So imaging, what this really means in radio astronomy is sort of like this. So if you are trying to look at your object through a really, really dirty window, it's been there for decades. No one's ever cleaned it. It's got so much debris on it. It's been through like 3 hurricanes, whatever. So you go to clean it, and you clean it really, really as hard as you can. You clean it as well as you can. But there's still going to be some splotches left over here and there, but you can mostly see the thing you're looking at through the window with this sort of filter. So that's what the process of imaging really is. It's cleaning your image as much as you possibly can to try to recover the true brightness of the object as best you can through all of the noise from the telescope, from the world outside, from in between you and the object that gets in the way. So those are the 3 main steps, sort of the bread and butter of synthesis imaging and radio astronomy. And supernovae tend to be point sources, and so the imaging is actually quite simple. So you go through the editing, you go through the calibration, you go and you get an image. Look, oh my God, there's our supernova, yay! So this is in the X-band, which is sort of in the higher frequency regime of, so it's around 40 gigahertz, and this is a deconfiguration image. So this is our lower resolution, sort of worse image. Great, there's our supernova. Yay, so beautiful, look at it. But oops, wait, that's not actually our supernova. If you just sort of double check the position of where we expect our supernova to be, it's in that purple box that I've highlighted there. That bright object that we see in the center of this image is NGC 1068 or M77, our supernova's host galaxy. So, oh no, that sucks. So when I first got this image, I ran up the stairs, I ran to my advisor's office, I showed them the image. I was like, oh my God, look, I finally did it. I got something. And they're like, oh, that's so great. Now go image the actual supernova. And I was like, wait, what do you mean? This is the supernova. She said, nope, that's the host galaxy. And so what's going on is that it's just so much brighter than the supernova that it's kind of drowning out our actual target, which is the supernova. So we might say, okay, maybe if we only look, the supernova is much dimmer than the galaxy, of course. So maybe if we try to only look at the very dim emission in this image, maybe we'll actually see the supernova. So, okay, let's try it. Oops, oh no, that just completely saturates our image. The galaxy totally floods into the pixels where we want to see our supernova, and it seems like there's nothing we can do, right? It's just sort of in the way, like, how can we get around this? It's there, it's in the image, we can't, what can we do? And why is this happening? So let's first address that question. So there's other than, of course, the galaxy being really, really bright, there's 2 main things going on here. So the angular resolution of our image is going to go as the wavelength of our observation over the separation of our individual antennas. So the shorter we make our wavelength, the better, which corresponds to higher frequency, the better our angular resolution is going to get. And the further apart we put our antennas, the better our image is going to get. And so I just have a little schematic here. We've got our array. We're trying to look at our supernova. This up on the top right is an earlier image of the supernova, a really beautiful image. And M77 is a really pretty galaxy, but it sort of makes it difficult to see the thing that we actually want to see for these 2 reasons. And so now I'll just show kind of how both the baseline, the separation of the antennas, and the frequency can actually really affect our imaging. So on this slide here on the left, I show an image from the shorter baseline configuration. And on the right, I show an image from the longer baseline. I should note these images are of the same right ascension and declination scale. So they're the same scale, and you can see just how much better the angular resolution is when we go to the longer baseline. It's so good, in fact, that like in this right image in the two boxes that are highlighting the galaxy and the supernova, you can kind of barely even pick them out. You would have to really zoom in to actually see the emission because it's just in so few pixels. Whereas in the shorter baseline image, the emission from the galaxy just floods out into all of these surrounding pixels. And then if we now go and look at low frequency versus high frequency image, we see that as we move to lower frequencies, the emission from the galaxy is going to get spread out across more pixels. And I don't know if you can really see, but even in this higher frequency image on the right, you can actually see the emission from the supernova. And then if we go and look at the faint emission, we can really see it's there and it's distinct from the galaxy. Whereas in the low frequency data, the galaxy just completely floods the image. So as you can see, there's quite a bit of variation within the data set that I was working with as to how much this host galaxy is a problem and how much it's going to affect our data reduction process. But that's not the end all be all. There are a couple of things that we can do in addition to the imaging that I talked about earlier that allow us to mitigate the residual emission from this galaxy. So the first one is self-calibration. This is when we actually, so I talked about calibration earlier, how we go and look at this like other object that we know really well. With self-calibration, it's this iterative process where we actually use the target object as our calibrator. And what this does is over many, many rounds of self-calibration, it really quite dramatically reduces the noise in our surrounding image and allows us to be able to better pick out individual objects in the field of view. The other method is called UV sub. It's kind of exactly what it sounds like. You take some region of your image and you literally just subtract the emission out of the image. And so if there's anything in your image that you don't really want, what you do is you self-calibrate it a little bit, you clean it up a little bit so you know that it's real emission, it's not some artifact, it's not fake. Then you subtract it out, and then you go back and do a few more rounds of self-calibration where you clean your actual target source. And so, and okay, just to show like kind of this if you look at this pre and post UV sub, in the pre-UV sub, in that lower purple box, we see the galaxy is there very obviously. And then if you look in the post-UV sub image in that purple box, that emission is removed. So that's how UV sub works. And with these two additional methods, we can pretty much mitigate the residual effects from the emission from the galaxy when we're going to look at our actual supernova. So great, we do all these things, we process the data, and now we can actually get values for the brightness of the supernova from our observations. So on this slide, I just show on the left a table of the actual values with their frequency and the time of observation. And then on the right, I show a plot of the frequency versus the brightness. And one thing to note is that we see that as we move to higher and higher frequencies, the data points tend to get dimmer, the brightness goes down. And so without even going into any modeling or anything, we can kind of expect that all of these data points are in the optically thin region of our spectrum. And I'll get into what that means in a minute. But another thing to say here is with these sort of observations, from a single observation, kind of regardless of how long it is, you get one data point. So here we have seven data points that came from 7 individual observations. So you kind of really need to do a lot of work to get enough data points to start doing some actual science. And any radio astronomer will tell you it's really hard to get telescope time. So even getting these 7 observations is pretty remarkable. So yeah, but great, we have these data points, we have the values for the brightness of the supernova. What can we do with them? So now we'll get into the little bit of modeling and some of the actual physics going on. So we have these values, like I mentioned, but we want to be able to connect them to some physical picture so that we can actually say something about the physical properties of the supernova that we're looking at with the observations that we have. So on this slide, I show one of the very good ideas for the physical picture of a core collapse supernova of this type. So core collapse supernovae will tend to happen in environments that have very sort of very dense gaseous environments. And so the supernova will explode. As we see in the center, the material from the star will start traveling out really, really fast, and it will collide with this gas that's sort of essentially standing still and create a shock. And you'll have these two things going on. You'll have a forward shock and you'll have a reverse shock. The forward shock, for the observations that we have, we kind of only care about the forward shock. That's the emission that we're seeing is coming from the forward shock. And so you'll have the forward shock, it's traveling through and coming into contact with this unshocked circumstellar medium. And at that front, that where it's traveling, you'll have all these instabilities, you'll have all sorts of wacky things going on that will produce this really, really strong magnetic field. And a little E&M review for those of you who have taken E&M or those of you who can look forward to taking E&M. When you have a charged particle that gets accelerated in a magnetic field, if it's really strong enough and you accelerate it up to ultra relativistic speeds, you produce synchrotron radiation. And so the emission that we're actually seeing when I talk about these observations that we have is not from the explosion itself. Of course, you can go look at that in the optical wavelengths. But what we're seeing is really the interaction of the shocked ejecta with the surrounding gas. And so, of course, when you have any emission process will come along with a corresponding absorption process. And so when we go to actually look at the emission from the synchrotron radiation, it's going to be affected by some sorts of absorption processes. And that will change how the final spectra that we get from the supernova looks. So I just wanted here to show a like real example where you can actually kind of pretty much see the forward shock and the reverse shock from the supernova. So this is actually a supernova remnant, Cassiopeia A. This is not our supernova CC, but I just think it's a really pretty picture, so I wanted to put it in. And you can see this, like, it has this sort of ring. This is a false color image, by the way. There's this sort of ring shape going on. Right outside the ring is the forward shock traveling ever on and on out into space. And then the inner sort of part of the ring is the reverse shock traveling backwards back to the center of the supernova remnant. So I just wanted to show that there as an example. But yeah, as I was talking about, when we have synchrotron emission, it will be modulated by some absorption processes. And the two primary sort of candidates for the absorption processes that it will modulate it are synchrotron self-absorption, which I'll call SSA because it's a bit of a mouthful, and free absorption, or FFA. So synchrotron self-absorption is the absorption process that goes along with synchrotron emission. It's an internal process when the same particles that were responsible for the original emission will reabsorb that emission. And so this formula that I put here is a formula for modeling the flux density or the brightness of synchrotron emission when considering self-SSA as the dominant absorption process. Now, free absorption, this is an external process. It's not something inherent to synchrotron emission, but it's just when you have some very energetic material interacting with some gas, that gas is going to absorb some of the emission from this very energetic material. And so, yeah, it's the absorption or the synchrotron emission gets absorbed by the surrounding gas in the supernova's very dense environment. And the formula on the bottom, which is slightly different from the SSA formula, is one that we can use to model the flux density given FFA as the dominant absorption mechanism for our synchrotron emission. So when we had our observations, we had our okay, let me say this first. So we have, like I mentioned, two data sets that happen about a year apart from each other. And so all of our data points are either going to be at that earlier time or the later time. And so there's not really much use in looking at the time dependence because two points in time is not really enough to model time dependence. So we'll take out the time dependence and say, okay, we just want to see how the brightness of the supernova is changing with frequency. And we'll take our data that we have that ranges across several frequencies and try to fit to both of these flux density formulas for both the SSA case and the FFA case. And we'll fit for 3 parameters in each. So the K1 and K2, which I've highlighted here, are just, we'll just modify like the amplitude of the flux densities. So so it's just, going to tell you, oh, is your emission like Jansky level emission or millijansky level emission? And then probably the really important parameter is that third one, which for SSA is P, the electron energy index. And that goes in the exponent of the frequency, so it's a power law. And then that's the same for free absorption, except here it's alpha, the spectral index. So those are 2 slightly different parameters, but they're very much related to each other. Alpha is just P minus 1/2. So we'll fit for both of those as well. And so how does that actually work? So we have our data points. I'm just going to go through an example with one of our data sets, so one of the observing times, and this is the earlier one, which was at around 1360 days. We take our data points, we go to Python, and Python has this great, or SciPy has this great thing called curve fit, which will allow us to give it some function, and it will fit for the parameters of that function and give us some like initial guesses for those 3 parameters that we're trying to fit for based on the data that we gave it. And so I list those initial guesses here. And we say, okay, like that's pretty good. We can see I've plotted how the fit actually does along with the data on this plot. It's pretty good, but like we want to try to do better. So we take those initial guesses and we put them in as our priors to do an MCMC analysis that will give us the best fit values and the uncertainties for these 3 parameters, K1, K2, and the electron energy index. And so once we obtain those best fit values for K1, K2, and P, we can then go and plot those again along with our actual data on this frequency versus brightness plot. So here I show in green is the best fit for the SSA at this earlier observing time, and the purple is the best fit model for the FFA at the earlier observing time. And the 2 big takeaways from this plot that I'd like you all to get, the first one is that if you look at all of our data points, which are in blue, we see that they either hover somewhere around the peak of both of our models, or to the right of it, where this is in something called the optically thin regime. And so to be able to really distinguish between which absorption mechanism is the dominant one going on, we would need even lower frequency data to be able to, if we had those lower frequency data points at those 2 vertical lines, which I've put on the plot, we'd be able to really quite definitively say, okay, it's definitely synchrotron self-absorption or definitely free absorption going on. So that's the first big takeaway. We've gone to lower frequencies than the original paper went. Now we need to go to even lower frequencies than that. And it turns out we actually have that data. We have data from GMRT at 0.6 and 1.3 gigahertz, which is on exactly where those vertical lines are on this plot. The other big takeaway is comes from the best fit values that we got for those P and alpha, the spectral index. We get a P of around 3.3 and alpha of a 1.2. Those are consistent with each other, but they're actually a bit steeper than what we would expect for type 2L supernova, core collapse supernova like this. Typical electron energy index is around 3. And so this steeper spectral index indicates that there's, in addition to the absorption process going on, that's modifying the emission we see, there's also a cooling process going on. That's really important because knowing that there's a cooling process going on allows us to also to get independent estimates for some of the physical parameters that we want to try to get out of this system, like the magnetic field of the supernova, the shock radius, and the mass loss rate, and so on. So knowing that we've seen, okay, there's probably a cooling process going on, so now we'll have multiple ways of trying to get at these physical parameters that we're searching for. And so on that note, I'll finally just talk a little bit about what we can do now that, or when we have these models for the flux density given FFA or SSA, we can go and say, okay, based on the best fit that we saw, we can go and look at things like the magnetic field, the shock radius, and the mass loss rate. Like I mentioned at the very beginning of this talk, as we look at a supernova longer and longer, we can say something about the mass loss history of the original star earlier and earlier into its lifetime. And so we're able to do these calculations, but we can't quite really say which one yet is the sort of more robust ones, because we won't be able to distinguish between SSA and FFA until we get this lower frequency data. So getting up to around 45 minutes here. So just to summarize, in our follow-up to the high frequency paper that came out and saw this original rebrightening, we saw a similar rebrightening in the centimeter wavelengths, or sort of mid-range frequencies in the radio bands. We're able to measure the magnetic field, the shock radius, and the mass loss rates at these two observing times, which are 1 year apart from each other, but we cannot yet distinguish between synchrotron self-absorption and free absorption as the dominant absorption mechanism for the supernova, and so we can't cannot say definitively which of our calculations for these physical parameters is really the more robust calculation. And finally, we see hints of a cooling process, which will allow us to then, once we go and look at the actual cooling frequencies and cooling timescales, give us independent distances or independent estimates for these physical parameters like the magnetic field, which will also help us to be able to distinguish between the dominant absorption mechanism. And so that finally kind of leads me into my future work. We want to finalize these cooling calculations and look at the lower frequency data. We also want to look at some X-ray data. So everything I've talked about here is all happening in the radio bands, but multi-wavelength astronomy is always the best way to go, and it can tell you so much more about your system that you're trying to understand than if you simply look in one band. And so if we look at the supernova in the X-ray, that can tell us some other physical parameters of the supernova that we cannot get from radio emissions, such as the temperature, the density of the gas surrounding the supernova, so on and so on. So we also have X-ray data that is basically just up to me learning how to process X-ray data, because right now I only know how to do it for radio data. And then some other future work is to just continue monitoring the supernova enough so that we actually also have enough data in time to fit for both frequency and time rather than just frequency. So that's where this is sort of headed in the future. The conclusion, I guess, is basically stay tuned until we figure out which absorption process is going on, and then we can say a bit more about the supernova. But yeah, one final thing So some of you may be familiar with this character that I like to draw, Sir Pulsar. Some other research that I've done, it involves pulsars, and so I really love them. They're dear to my heart. So I like to draw this character. And after this summer, I introduced a new character to the family. Sir Pulsar's mother, actually, Madame Cecilia Nova, who likes to go by Cece. And so, yeah, I'd just like to introduce you all to Cece. And thank you very much for listening. Yep, yeah. Yeah, Shane.
Um, so for the data that for like the previous like if you go back where you're talking about like the processes you did like with the imaging and like everything else, you were talking about like deconvolution, right? What are that deconvolution is like a matrix multiplication, right? You're trying to take out a transformation caused by like some sort of thing. What are you trying to take out? Is it like rotation rate of the Earth or something, or is it like something else?
Yeah, that's a great question. The deconvolution, you're exactly right. We're trying to, so the actual when we do synthesis imaging with interferometry, what the telescope actually gives us is a convolution of the true sky brightness and all of the noise inherent to the telescope. Well, yeah, the noise inherent to the telescope really is what it gives us. And so to get back the true sky brightness, which is what we want, we have to deconvolve with the best we can do with modeling for the noise from the telescope. So that's what the deconvolution is, yeah. Yeah, in simple terms, it's really um it's that's a very clean way of putting it, but in reality it's not a very clean process. It takes a lot of rounds of deconvolution that goes through these major and minor cycles. Yeah, we could get into it more later, but yeah. Yeah, great question.
So I just wanted to ask, you guys are observing more of the forward shock or the outward shock, but the inward shock, if that's kind of collapsing in on itself, could that possibly cause another event, like as it like, because it's going all inward, right? Would it converge on like a singular point and cause a different event happening, or is it too weak?
So, as far as I know, I've never heard of anything like that. I think it's probably what your intuition is, that it's too weak for any like significant event to occur. We definitely can see emission from the reverse shock, which it can also be very enlightening, specifically in the X-ray. But yeah, so one thing that happens is like a couple in the years post supernova explosion, it will still be called a supernova. It will be this active thing that's actively emitting. And we can see the emission in the radio, in the X-ray, and all of these wavelengths. But as both the forward shock and the reverse shock travel through the circumstellar medium, they'll sort of like a shovel start like picking up the matter that's there, and it will start slowing the shocks down to the point where it's not really energetic enough anymore to produce any emission. And so my best guess, again, like I know a little bit less about the reverse shock than but my best guess is that that like picking up of materials slows the ejecta down quickly enough that like it sort of just becomes like kind of very low energy, and then it's just kind of there at some point a couple years after the supernova, depending on how energetic it is. And then at that point we call it a supernova remnant, which are also still very interesting to study in certain ways. But yeah, I think so the ejecta sort of just starts slowing down over time. And so at a certain point, it's just kind of there. It's not going to do anything big. I don't know. Yeah, if that answers your question, maybe. But that's a great question.
Anybody else? Oh,
All right. Thank you so much for your talk. Like, this is such a fantastic, like, well-made presentation. This is so amazing. So I wanted to ask about the SSA and FFA fits, like specifically like what science questions is answering. And like, like when you presented like the supernova in the beginning, like I thought, one of the major science questions is like, why is there this rebrightening? And so do the SSA and FFA fits help answer that? And if so, how?
Yeah, I think for the SSA and FFA fits, it is important for us. Well, yeah, yes, it does answer that science question. And one of the ways in which it does that is that depending on which absorption mechanism is going on, or I should say the other way around, the physical attributes of the supernova, like the magnetic field, the radius of the shock, the speed at which the shock is traveling out, and the density of the surrounding medium, the temperature, just to name a few, will determine what absorption processes are more dominant than others. And so in that sense, I should also say the mass loss rate, importantly. So in that way, we kind of have to work backwards. We can say, okay, like we know what the spectra from the supernova would look like if we saw this absorption process versus this one. And if we can say that, then we can then go to say something more concrete about these parameters I mentioned, the magnetic field, the mass loss rates, and so on. And and that will allow us to like rebuild this sort of physical picture of the supernova, and importantly, like the mass loss history of the progenitor. So like when I say mass loss rate, like when we look at the supernova sometime after the explosion and we get a value for the mass loss rate, that's like, so like, for example, looking at this supernova 1,000 days-ish after explosion tells us we can get these, these mass loss rates that I show here are gonna tell us the mass loss rate of the progenitor star at around 1,500 years pre-explosion. And these mass loss rates here, I didn't go into them because we don't really know yet which one is kind of more correct. These are very different. But if for example, the FFA ones, which are 10 to the -3 solar masses per year, roughly, that is much, much higher mass loss rate than would be possible to get from if the only mass loss mechanism were from thermal pressure, from the thermonuclear reactions in the star. So that would tell us, okay, we then need to go think about what other mass loss mechanisms are going on. The main one, which could be binary interaction. And actually, the mass loss rates can also tell you about the orbital separation of your binary system. And so, yeah, that's how, like, so we sort of need to work backwards from figuring out what the absorption mechanism is to then going and trying to connect it to these physical pictures. So yeah, I hope that answers the question-ish.
oh yeah, let's check the Zoom real quick. Question from Lucas Lawrence. Look at that. And Lucas asks, what else could the dominant absorption method tell us, / what are some implications it would have about supernovae and their remnants? Awesome talk, by the way. Thank you, Lucas. We love you.
Hi, Lucas. You should come visit. Okay, but for those who don't know, Lucas is a Cass alumni, Cornell alumni, alumnus. But yeah, I guess maybe that was sort of, I guess, what Stella was asking too. But yeah, the dominant absorption mechanism would help us sort of piece together the mass loss history of the progenitor star. So that's when I'm going and talking about, trying to distinguish between SSA and FFA. It's with that goal in mind, although it seems muddled because it's a few steps back from actually getting those, looking at building up that physical picture. So I hope that answers the question. But yeah, thanks for attending, Lucas.
All right, we got one more, and then we're gonna cut it after you, just because it's around 8.
Out of curiosity, what's like what type of software did you use? I might have missed it or something, but just yeah.
Yeah, it's not letting me go back to the slide, but it was all okay. So the data processing happens in something called CASA, which is Common Astronomy Software Applications, and that's a software that's developed by the NRAO to do like all of their data processing. So, but CASA actually, like the language that you, I guess, talk to CASA with is Python, and then all of the modeling happened just in Python as well. So yeah, but CASA. I don't know if like you can get it on your like own laptop or something, but yeah. Yeah, so I spent a lot of my summer learning to use CASA. Yeah. Yeah, sure.
And how long did like did the processing take?
It took a long time, and it's not done because there's more observations, and you can always do more cleaning. So yeah, and like it's something that I was new to, so I also just had to learn how to do it, which definitely added on to how long it took. But yeah, and like we saw with this, so the higher frequency data from this paper that originally saw the rebrightening didn't really like their data reduction. They literally just ran it in a pipeline. They didn't have to do this kind of like specialized cleaning, because when you're dealing with high frequency observations, like the residual emission from the host galaxy like doesn't really contaminate your supernova emission at all. So they could just run it through a pipeline. And like I mentioned, supernovae are point sources usually, and so they generally are easy to image. But because we have this really bright galaxy and we're dealing with lower frequency data, I had to do each observation individually. So that took a while. Yeah. Thanks for the question.
All right, so thank you all once again for coming. Just a brief closing statement. This lecture series, we're hosted by the Cornell Astronomical Society, or CAS. A lot of you are members, so you know what that is. But if you don't know what that is, we are a undergraduate organization here, a student-run organization that we host open houses at the Fuertes Observatory every Friday, which is today, from 8 p.m. to midnight. Unless there's horrible, terrible weather, we'll be there. So we're gonna go walk to the observatory right now and start our open house. You're welcome to follow us or do whatever you want. And we'll have more lecture series in the coming weeks. So thank you very much for coming, guys. Bye, guys.
Hi, Lucas, and my parents. Yeah.
Hi, Gillis's parents. And Lucas, I guess.
And Lucas. Have a nice night, everyone. Bye.